Dr. Jin-Guang, Dr. Elizabeth Lee, and Professor Andrew Geim, and also Professor Harvey ALTER, distinguished guests, and friends from the research community. We gather here to have this special event together with scientists. I'm the Associate Director of PolyU Academy of Interdisciplinary Research, and I'm also a Chair Professor in Systems Biology and Artificial Intelligence. So I will be the host for today's program. So today we are extremely honored to have two Nobel laureates here with us to share their experience and thoughts with us. But before we start our program, let me invite our president, PolyU President, Professor Jin-Guang, to stage to give some open remarks. Welcome.
Dr. Elizabeth Lee, Professor Andrew Geim, Professor Harvey James ALTER, Professor Zhang, Mr. Dai Jian, Professor Shen Jinhua, Ms. Zhang Rui, distinguished guests, colleagues, students, ladies and gentlemen, good afternoon. On behalf of the Hong Kong Polytechnic University, it is my great pleasure to welcome you all to this very important and meaningful event called Together with Scientists. This is the thematic event. This is a highlight of the 2025 Hong Kong World Youth Science Conference, jointly organized by PolyU. This event by PolyU and the Hong Kong Alumni Association of Beijing's universities. I would like to extend our profound gratitude to the association for partnering with us on this meaningful event. And we extend our special thanks to Dr. Elizabeth Lee, the president of the association. Maybe can I invite President Lee to stand up so we can give her a round of applause. So we are exceptionally privileged to have two Nobel laureates and plus other world-leading scientists as our esteemed guest speakers and participants today. And these two Nobel Prize winners, of course, they have been introduced to you already. We are Professor Andrew Geim. I will not ask him to stand up. They will appear on the stage later. And who is the Nobel laureate in physics, and Professor Harvey James ALTER, Nobel laureate in physiology and medicine. But I do invite you to give them a round of applause. Without, I don't have to explain how important their contributions have been. The fact they have won a Nobel Prize, okay, this is the highest honor of any scientist, for any scientist. So it's testament to their achievement, contribution to science. But I guess what's even more important or interesting to you is how they made it, how they worked hard, how they persevered to overcome difficulties. And I'm sure you can learn a lot from their sharings. At PolyU, of course, we are very, keen on further developing our research, because over the last few years, our research has advanced a lot. In fact, 5 years ago, compared to 5 years ago, our research staff has more than doubled. Our research funding, external research funding, has also more than doubled. And we have set up a lot of research institutes, centers, and one of them is called PAAI, the PolyU Academy for Interdisciplinary Research, which is co-hosting this event. And some recent developments we have undertaken include the setting up of the PolyU Academy for Artificial Intelligence. Now this one is the acronym is PAAI, PAAI, PolyU Academy for Artificial Intelligence. In fact, the director, Professor Yang Qiang, just joined us on the 1st of April. He is among the top 5 or 10 leading AI scientists among the Chinese scholars worldwide. Our executive director for this research institute is called Yang Hongsha. And she gave a presentation 2 weeks ago. There was 40,000 people, no, 400,000 people on the online listening to her presentation. So very impressive. She was the chief scientist of 2 major large language models. One is Ali Qianmeng, the predecessor called M6, and the other one is called Doubao. Okay, so some of you may have used Doubao and Qianmeng. We are also in the process of, preparing for a interview to win the opportunity to host the 3rd medical school in Hong Kong at PolyU, and AI will be a major enabler of the pedagogy and the skills set for the 3rd medical school. So with all that said, I wish you all an enriching and memorable experience at this special event. I apologize that I will have to leave because I have 2 other delegations who are coming at 15 minutes interval. So I would have loved to stay on and listen to the wisdoms of the 2 Nobel Prize laureates, although I know I have no chance winning one, but at least it's good to hear their stories. So apologies. Thank you so much.
Today's event is joint organized by PolyU and the Hong Kong Alumni Association of Beijing University. So we really appreciate the opportunity to join organize this event. And also this event is also part of the series activities of 2025 Hong Kong World Young Science Conference. Okay, so we are delighted to help to host this event here. And to capture today's unforgettable moment, and the 2 organizers prepared some souvenir. So I will invite Dr. Lee and Professor Teng to come to stage, exchange souvenir. That's before real event. Take some group photo. Professor Teng, Dr. Lee, and Professor Gay. All right, so we now get to the most waited moment for our 2 speakers to share their thoughts and their experience with us. So the following session will be moderated by our Associate President, Professor Wang Zuankai.
Ladies and gentlemen, I'm pleased to introduce the first speaker of today, Professor Andre Zhang. I think everyone wants to win the Nobel Prize. The answer is to work hard, but this is only the part of the answer. I think the true answer should be like to work. Last year, on June 21, 23, Professor Andre, 24, yeah, you have a very good memory, 24. Professor Andre Geim visited our PolyU. Remember vividly, even at last day, Professor Andre still listening to the talk. This is very, very unusual. Usually after with the Nobel Prize, we don't want to do research anymore. And also, at age 33, the H index of Professor Andre is 3. But finally, he won the Nobel Prize. I think probably you wonder why he can win the Nobel Prize. Because he invented the wonder material. Now, let's welcome Professor Andre to deliver the talk. The title is Wonder Materials.
We are short of time. I have only 10 minutes, but I can't skip saying that it's my 2nd time in 1 year being here, and it's a great pleasure to see especially my hosts from 9 months ago, Professor Wang. Last time I was here, I was given a talk about my recent work, which was only 5-7 years old. It was about microfluidics. Today I'll give you a talk about generally what the Nobel Prize was for, at least how I understand this. Okay, So if we look around ourselves, we are familiar with three-dimensional worlds. Everything around us has 3 dimensions. It would be width, length, height, and so on, until just this century, this millennium, we as the human race didn't expect that materials where one of those dimensions, say thickness, would be essentially absent, that those materials exist. And the reason for this is because there are very powerful theorems which prevent growth of materials in 2 dimensions. Everything in our 3-dimensional worlds like to have 3-dimensional architecture, and it's impossible because of thermal vibrations essentially to grow 2-dimensional materials. So our research in this direction asks with a very simple question: how thin we can make graphite? You know, Greeks 2,000, 3,000 years ago, probably from Plato's school, asked themselves how thin you can make material. And they speculated at that time, you take a stone, chop it into 2, then chop each part into 2, and then divide by 2 and 2 and 2, and eventually they came to the concept of an atom. This atom was essentially mean indivisible, something very small. So that's essentially what we have made. We took graphite. This Gedanken thought experiment was made out of graphite. Divide graphite, piece of graphite, you know, it's like mica. It's very easy to split into 2. Only we didn't obviously split big parts into 2. We used Scotch tape, put it on the surface of graphite, exfoliate it, and here we are. There are thin flakes of graphite, like in pencil trace, on the surface of the Scotch tape. You look in the optical microscope on the transparency, and you see that somewhere here there are transparent pieces. It's a metal graphite. It's black because light doesn't come through, but in optics, when you see something metal transparent, it means it's very thin. So essentially, yeah, we manage with that simple technique make very thin pieces of graphite. It's not yet on this image as 1 atom thick, but it waited 2,500 years to make this Gedanken thought experiment and reality. So you can use other kind of techniques. Here you see on this image something millimeter size, and it's kind of bluish, and this is a single layer of carbon atoms visible by naked size, by naked eye, and of course we can use all-powerful techniques which we have these days, like transmission electron microscopy, for example, and we do see crystal lattice. We can prove that it's in single atomic layer. So sometimes people ask a question, so graphene, so what? It's extremely simple structure. Carbon atoms in this hexagonal lattice arranged around, and my answer, not initially, but these days, I believe that the most remarkable thing about this structure is that it exists in our world, where we have oxygen, where we have water in atmosphere, and whether we have temperature. Try to do the same with, say, gold, platinum, or any of those refractive metals which do not melt. Actually, you can't do that. They will disappear beyond a certain thickness of, say, 100 atoms it's impossible to make most materials because they don't like to exist in two-dimensional forms, island growth and so on, for those who are familiar with crystal growth happening there. If it would be all that we managed to extract two-dimensional materials, it would be interesting, curiosity, but I would be not standing here today. So after this original observation of very thin graphite pieces down to a single layer, we start looking at the properties of this material and found that there are a lot of surprising wonder properties of this one. You don't expect this because graphite, we know everything about graphite for 100 years, and you generally expected properties of one layer would be similar to properties of the parent materials. It turned out to be not true. It turned out that reducing dimensions brings a lot of superlative properties. And actually, the Nobel Prize was given somewhere here in the middle about electrical properties of this material, not even for the whole stuff which we and other group have studied along the way. So now, 20 years after initial work about this, we know tens, hundreds, nearly 1,000 of different materials, which are one atom or one molecule thick. Essentially, I'm pretty sure in this audience there are people who work on two-dimensional materials or learn about this. Okay, about this. So if I look what was with condensed matter physics and material science 20, 30 years ago, everyone who worked in this area knows how strongly reshaped all those areas. And actually, even biomedics these days sometimes use graphene and other two, mostly graphene in their studies. So, but I don't have time. It's too big area to discuss about what graphene and two-dimensional materials brought to science. So people often ask, okay, what it is good for? The proof is in the pudding, as people say. 20 years in terms of material science, it's a very short period of time, but still now some applications, mostly of graphene, nothing yet from two-dimensional materials, are coming. Just 10 years ago, we were working with this Scotch technique, picking up those small pieces. It's the dominant weapon of scientists around the world, pick up high-quality crystals of graphene used all over the world. But recently, 10 years ago, people start producing graphene in square kilometers and in tons. After that, it has become possible to talk about applications. And they gradually come in, and now after initial high value of disappointment, now there are more and more applications coming. There are plenty of products. I know about 100 of different products which incorporate graphene already, improving properties of those products. It's not revolutionary. It just slightly, for example, improve quality of skis or helmets, and running shoes, for example, can be twice longer. Huawei, for example, has nicer touch screen due to cooling technology, graphene cooling technology, and so on. And some more bigger applications is coming. How many people in this audience have an electric car, for example? Not one, probably. Half, although please raise the hands. Two, I can't believe. Two people in the whole audience. Okay, now your parents probably, if students there, have a car. So as many people have driven an electric car, drive an electric car. And if you have a car, you should be aware that you are using graphene. It's an additive which is routinely added practically to all lithium-ion batteries in cars and in other manufacturers for other applications as well. It increases your driving range only for a few percent, but this is how it improves our life. It's several miles on your clock, which is there. So it's real applications, and you probably were not aware about this one. It's also, there are big applications like motorways covered with graphene-enhanced asphalt, tarmac, and entire fleet, for example, in ships in Finland are now painted by graphene-improved coating, saves about 10% in energy costs. So applications coming gradually, but inevitably coming, and it's the beginning. It's the beginning even for graphene and two-dimensional materials, which were, again, we were not aware about this whole class of the materials just 20 years ago, are strongly coming. And the longer you live, the more applications you will see. It's the beginning. Thank you.
Next, I would like to introduce Professor Harvey ALTER. I think, for us, we want to publish a good paper, but I think more important is to tackle the global health problem. For that, Professor ALTER was the first one to discover hepatitis C virus. This virus is very, very special for Chinese, because many Chinese people suffer from HCV. Professor ALTER won the Clinical Lask Award in 2000, and then with the Nobel Prize in medicine in 2020. And today he will give very general talk about the thought to university students. And Professor ALTER is also the poet. He will share his poem to us. Welcome, Professor ALTER.
Thank you for inviting me here. I like talking to young students. I'm not going to tell you how I won the Nobel Prize. That's not my job today. I'm not sure how I won the Nobel Prize, truthfully. But my job today is to talk to you about science and how I got into the position to win the Nobel Prize. Because I didn't have much time, I'm going to show you slides at the end, a few slides at the end. But basically, when I was a teenager, I knew that I wanted to go into medicine. Not science. I did not want to go. I never thought about research. I thought about being a doctor, having a stethoscope, seeing patients, and that was my goal. And I went to medical school, University of Rochester. I loved medical school. I was planning again to go into clinical practice. And the point of what I'm going to tell you is that you can have plans. You all have some plan of what you want to do. But sometimes your plans don't work out. And then you get an alternative. And sometimes the alternative is better than what you planned. And that was true in my life. Again, I'm heading towards clinical practice. When I was a resident at the medical school at Rochester, I got a letter from the US government. And it said, "Greetings, you have been drafted into the US Army." This was a time when there was a draft in the US. This particular reason was a crisis in Berlin. Now that was going to upset my plan, because if I went into the Army, my life would have gone in one direction. But I had already applied to the National Institutes of Health, where I would do some research. With a lot of help from my mentors at Rochester, I was able to get to NIH before I had to report to the Army. That was a life-changing event. If I went to Berlin, which is where I would have been sent, it would have been fine, but I would have gone into practice, clinical practice for sure. So now I'm at NIH and I had to figure out what to do. I had to come up with a project. I'm not going to go into the project in detail, but just by chance, I was studying why people who get transfused sometimes get febrile reactions, get chills and fever after transfusion. Knew some of that was due to antibodies to red cells or antibodies to white cells or platelets. I was looking to see if it could also be due to serum proteins that were different than your own. And to look at that, I set up little agar plates and reacted multiple samples from multiply transfused people to just normal people to see who might have an antigen different than somebody else. To make a long story short, we did find an antigen. I got to work. Somebody said to me, you know, there's a guy in building 5 who's doing exactly what you're doing. He's setting up agar plates. He's looking for antibodies to serum proteins. He's a geneticist. So why don't you go see him and see if you can collaborate? So I went there, and within a day, we had a collaboration. It turns out we found an antigen in serum that was called the Australia antigen because we found it in the serum of an Australian Aboriginal. Over a long course, my mentor at that time, Dr. Blumberg, kept pursuing this. I went back in to finish my residency. Turns out that Australian antigen turned out to be the surface coating of the hepatitis B virus. We go fast forward a little bit. I'm now at Georgetown University doing a hematology fellowship. And I applied for a practice position in Washington. And I didn't get it. And I was very disappointed. And so my boss said, you know, you can always go to practice. Why don't you stay here at Georgetown? And which I did. So again, that was a second changing point. It was failure. It was failure to get the job I wanted. But it put me in a different direction. It put me in a direction of academic medicine, which I enjoyed. And then I didn't want to go into practice anymore. And then I got a call back to NIH 3 years later, because they said, you know, that Australia antigen you were working on as a fellow is now very important. It's now a virus. Do you want to come back and work on it? And I jumped at that opportunity. So my life changed in 2 ways. One, the draft and not going in the draft. And 2, being rejected in practice and getting another route. So again, the point to you young people, is do make a plan, have a course in your mind, but be ready for it maybe not to work out exactly as you planned it. And you can make the best of what the alternative is. In my case, it worked out very well. So this morning I presented the whole Nobel story. I don't have time to do that today, but it led to the discovery of the hepatitis C virus and the potential now to cure the world of hepatitis C. But now, if I can have my slides, just going to show 3 slides. That one. This is probably the most important. This was sent to me as a congratulatory card after I got the prize. And it said, there is no elevator to success. You have to take the stairs. If there's nothing else to remember from my talking today, it's this. You don't jump to success. You go step by step by step. You find a starting point, and that leads to the next step, leads to the next step. If I went through my whole lecture, you'd see all those steps that went into my life. So remember that. Next slide, please. So this is my roadmap to success, if you will, possible success. Next. So my lessons to you are, you have to work hard as if your career depended on it, because it does. In China, working hard is what you do anyway. So I probably don't have to encourage you in that way. But when you start to get into your career, you want to find a mentor. You want to find somebody who's going to start you off, somebody whose lab you're in, who's interested in you and your advancement, not just wanting your hands to help on experiments, but really to foster your development. That's so important. Once you start your research, you want to be collaborative, not secretive. You want to share. You want to share your data. You want to get collaborations, and every collaborator that you get becomes sort of a new mentor. They teach you something else. I don't know how to emphasize this anymore, but collaboration was so important, Michael. You can't these days know everything. You have to, science is so advanced that you often need some help. You need somebody to collaborate with to improve what you can do. And that was critical for me. Oh, sorry. You want to be observant. We pointed out at the meeting we had in Hong Kong that most big experiments are not because you say, I want to discover this, or I want to discover that. It's because you made some observation that intrigued you, and then you pursued that. In my case, at Oregon, we found this silly little line in agar gel. Had no idea what it was, but kept at it until it proved to be something important. So I encourage you that if you find something in your research, keep after it until you prove it's really nothing, but maybe it's going to progress into something. You have to be persistent and not give up right away. Don't be discouraged by early failure. Experiments fail all the time. You can't take it personally. The resilience from failure is a big part of research. That's a good lesson, truthfully, and it was certainly in my life. And then lastly, don't be afraid to take chances. You can follow what's already really proven and reprove it. But if you want to be really find something novel, you got to take a chance sometime. You got to observe it and then pursue it and take a chance, because big science comes from small observations. And you don't know where they're going to go. So I leave you with this. More than anything, perhaps, is show wonderment in the world around you. Remember this picture of this little girl watching the hedgehog and the wonderment in her eyes. When you get discouraged, think of this hedgehog, think of this little girl, think of what she's thinking, and be inspired by it, because observing the world, observing your experiments, observing little things that don't make sense to you, but soon they might make sense to you. So I leave you with that thought. So I can answer questions if we have time.
Thank you very much, Professor ALTER. I think the roadmap to success are very, very insightful.
Thank you.
I take all the notes. Okay. Our two guests, the sharing, cover various aspects of science. I'm sure that many of us here want to hear more insight from our two Nobel Prize winners. Now I will chair the panel discussion. Ladies and gentlemen, my name is Wang Zuankai. Let me first explain my English name. Zuan means deep, Kai means thick. So Zuankai means deep thick. So that's my name. Okay. It's a privilege for me to host today's panel discussion precisely because I'm just 1 meter away to two great scientists who have won 3 Nobel Prizes. Probably people wonder why we have 2 scientists but 3 Nobel Prize winners. This is because Professor Andrew Geim won the real Nobel Prize and also won the Eagle Prize in 2000. Right? Okay, Professor Geim, your work are truly art of playful discovery, from making graphene from sticky tape to floating the frogs. You even include your pet as a co-author in a paper. Your discovery shows that great idea and a breakthrough can come with fun simultaneously together. But today, science and fun seem to be more and more mutually exclusive because funding agencies pay more and more attention on application-driven research, which is not fun to some extent. So now the question is, can you offer your insight to young scientists today? Should they work on curiosity-driven work, which might be difficult to get funding, or they should focus on applied research that's probably easier to get funding?
Yeah, thanks for this question. It's rather difficult to answer it, but I only partially agree with you that it's difficult to combine fun with work, because work is an important part of our life, and if you get bored at work, you probably should change your specialty. So my work is one of my hobbies. I love working in the lab. I even hate it, but then I like even writing papers, which is the most hateful part of any scientific process. So it depends on personality. So if you love your work, you will find some fun in this work. You go to drink coffee with your colleagues, you smile, you do something, but probably what is important you can try to do is all my work, I usually give 3 examples. Actually, there were more examples. Most impactful work was not the one which I got grants for doing was. So essentially, the trick is you apply for grants for the work you have already done. Then your referees and everyone is happy. If you put something extremely new, people would say, oh, it's impossible or it is rubbish. For example, would I get any grant for levitation experiments? Never. People say it would be silly, but it was big impact. Would I get any grant for what I describe you, making very thin pieces of graphene, of graphite, go to graphene? Some people would say impossible. Other people say, so what for? even our first paper with all the results about electronic properties, it's had hard time with referees. They say, oh, so what? Okay, so essentially the trick, apply for the work you know well, you've done, but in the meantime, put some of those resources which granted to do something you really want outside, presumably your area of expertise. Try to collaborate with your colleagues nearby and try to find something new outside of your area of expertise. So sometimes when people say, oh, we do research, I'm saying, I hate research, because research implies that you research where other people searched before. So try to search for something new rather than research.
Thank you. Perfect game. I like your writing on random walking. I think very, very insightful. That writing gives me many insight for me to how to do research. And also your answer echo the point raised by Professor ALTER. Professor ALTER, you mentioned the big science come from small observation. I think you too reach consensus on how to do research. Okay, so the second question, now it looks like everyone is moving fast. Fast food, short video, and quick research. But on the other hand, doing science slow can be rewarding and pleasurable. In 2006, slow science movement started as a call for healthy and better science culture. The movement have gained momentum over the past years. A true master for slow science, I think, is Professor ALTER. Professor ALTER, you spent 20 years finding HCV. We are very touched by your persistence and slow science. I remember you had ever wrote a poem which says, if we don't publish soon, they will find us. So Professor ALTER, shall young scientists achieve slow science by sticking with difficult problems for years or choosing quick science so that they can easily survive? Could you offer your advice?
Yeah, I think so. Yeah, I'm a big proponent of slow science. It took actually from the time we first observed that there was probably a new virus that was causing post-transfusion hepatitis. The time when that virus was actually cloned and identified specifically was about 15 years. By the time we got to a treatment and an ability to cure hepatitis C, it was closer to 40 years. And as Andre said, if you put in a grant and said, I want to do this study, it'll take me 40 years to do it, you are not going to get granted. So what you do is you have either a hypothesis or a idea. I want to look at something. In my case, I wanted to look at the causes of post-transfusion hepatitis. I didn't propose that I would discover a virus in that process. That came without any foreknowledge. I just said, well, let's look at post-transfusion. Let's find a population that is heavily transfused, that has a big risk. Let's follow them very closely every week for 12 weeks and then up to a month. Let's see what happens. How many people get hepatitis? That was the starting point. Then when you find out that a lot of people were getting hepatitis, you say, well, what was that due to? How could they get, why were people transmitting hepatitis when they were donating blood? Then we found that the certain donors were more risky than others, and we got rid of those donors. Then we had a chimp model, and we could transmit the virus to the chimp. And then we could take the virus or take the infectious inoculum and perturb it. And show that there must be lipid envelope on the virus. Then we could filter it and we could say it must be a small virus. Then if it's small and lipid envelope, it's probably a small RNA virus. The point is that research is incremental, step by step, what I showed you. You don't know where it's going all the time. But if you get some hints that it's going somewhere good, you keep at it, you keep at it, you keep at it until it happens. Now, whether you get funded all that time, that's a different story. At NIH, we had internal funds, so I was able to do this long study. I don't know if I could have done it anywhere else. And the other point Andre made, and I want to reemphasize, is you have to enjoy your work, you know? So many people in this world work and it's just a chore to go into work. But in sciences, it's continuously exciting, whatever field of science you're in. And I, like Andre, always enjoyed coming to work. I enjoyed talking to colleagues. You got to get some positive feedback along the way. But that, and you always wonder, well, how will I get to the next idea? Well, it just kind of comes to you. You find something and that leads to something else, leads to something else. And the ideas keep flowing as long as you keep at it. So slow science has its place.
Thank you, Professor Andrew. I was very impressed last year. I mentioned during the conference in the last day, you still listened to the talk. This is very unusual. So being interested, what's the initiative for you to keep up the good work? By saying so, I remember, you know, every year you continue to publish paper in Nature Science. This is also very unusual. So what's the inner desire for you to continue to produce good work?
Yeah, I guess I'm an adrenaline junkie. In this case, one of those things which give me a lot of adrenaline when a referee report comes with some negative comments, and each time when a paper is accepted, I'm playing this game, publishing in prestigious journals and so on, rather than putting them in the secondary. So in this case, you hate this game. On the other hand, each time when the paper appears in Nature and Science, and those who published in those journals, they know it's a battle won. Yet another battle won. You're happy with the outcome, but this is kind of one of those superficial but still very important motivations behind doing this, being competitive, being proving that you're still there. But on the other hand, there is another even bigger element which scientists here also know. It's not only winning the competition, it's the process itself. And I think being a researcher, scientist, in one of privileges, the best privilege you can get in your life. It's better than having a lot of money. Money is just paper, but when you have interest in your work, is really something inspiring. You essentially science and research is like a multidimensional chess game. Go or just simple chess, and for me, I can compare research with making a puzzle. You know, those puzzles where you get 1,000 different pieces of puzzle and eventually you make this puzzle. But research is not a puzzle where all those pieces do exist. You are given, say, 25% of those pieces and you put them together. And the one who wins the competition is the one who makes the correct picture, the answer of the whole puzzle from the minimum amount of pieces. So everything at the back of your mind is running all these process, what it could be, etc., etc. It's very motivating and solve those problems which are much harder than solving whatever puzzle or wordle these days. It's interesting. It makes your life full.
Thank you.
Just add a
Okay.
point if I could. Something I didn't mention and something you're going to find you'll run into. I told you to work hard, but working hard is a contradiction to having a good family and a good relationship. Finding a balance between your family and your work is maybe the hardest thing you will face. It's I can't tell you how difficult it is because you want to work all the time. And yet you have a wife or a husband, you have children. And how do you give them the time that you give to work? And just keep that in mind. You have to find a balance so that work doesn't become your entire life, because your family is equally important or more important. And the older you get, the more you realize how important the family is.
There is a solution for that. Marry a scientist and make your children scientists as well.
That's another.
As I have done.
That's another option.
I totally agree. I think being balance is the key.
Yeah.
Okay. So Professor Alter, you just mentioned there's no elevator to success. We have to take stairs. I think in everyone's career, we always encounter difficulty. So my question is, what's the largest difficulty and what's your secret to tackle this kind of challenge that paved the way for your Nobel Prize?
Yeah, I don't know there's really an answer to that. I never thought about a Nobel Prize. I'm always asked by students, how do I get a Nobel Prize? The best, and I'm basically a clinician, clinical researcher. So clinical researchers don't get Nobel Prizes. It kind of happened, but nothing I ever thought about, truthfully. But the way I got it was those steps. You just have something you're looking into, and that tells you, well, this is the next step you should do. And then you find something else in the same area, and you keep going. And as it turns out, with other collaborators and people who developed the drugs, the whole story fit together: discovery, cloning, treatment. The whole story is what made the Nobel Prize, and I was part of the beginning of it. So I don't know anything else except persistence, and you have to use your head, but you often cannot predict the outcome.
Okay, one more question for both of you. Recently in PolyU, we launched a new faculty of computer science, computer and mathematical science, basically AI. So how do you predict the AI for science?
Well, I have not yet used AI, I know my own intelligence is artificial, but I have not applied it yet. It has great potential. This meeting we're at really encouraged me to get into AI, but I really cannot speak to it because I haven't used it.
Thank you.
Yeah, I use what they called AI on a regular basis. Of course, it's not artificial intelligence. It's a very smart computer program. And I do not share either excitement or scare about AI because I know how it essentially works. That's probably the difference. It's just pattern recognition program, very complicated, but it's simple pattern recognition, nothing more like when you look on your phone and your face is recognized, phone recognizes you. You don't think that this is intelligent, but the same happens with the sentences you say on a more complex manner. So it's like a very complex program. I think we are at this stage where the stage of a big hype. Imagine 50 years ago, someone gives you just a phone and oh, marvelous, it's so intelligent, it can call someone at another place. So because it's so complex, like computer, have you ever thought how a computer from transistors who switch from 0 to 1 can create all those complex images on your computer screen and so on? So it's similar because we do not really follow every step from zeros to 1 from transistor switching the similar way how our sentences are answered by pattern recognition through a huge library of patterns which exist in language models. So in a similar way, it gives us kind of mystery and wonder, but in fact, it's a very useful way. It's a revolutionary way, similar to personal computers, what they made, similar to what web browsing. We never go these days to a library to look for information. It's at our fingertips. Similarly, in more intelligent way, all this information is summarized now by these large language models. It's great, but it's not intelligence in a sense we understand it. At least it's not living intelligence. It might be coming, but it's not in the near future.
Thank you. Any question from the audience?
A postdoc fellow from, oh, thanks. I'm a postdoc fellow at PolyU, and I got my PhD from Carnegie Mellon 2 years ago. So even though Professor ALTER mentioned that like you need to make plans and as best as you can before you make decisions, but usually ultimate plans can be better sometimes. But I wonder, like, what do you consider when you make plans, especially at the earlier academic career? Maybe this question can be both of you, like, you know, any tips, any thoughts for a young scholar? Thank you.
Yeah. Well, it's a hard question to answer. You know, you do have to set a direction. You want to set a course. This is what I want to do. I want to get somebody who's going to really help me advance. So that's the mentor aspect of it. So then you get into the project of that mentor and you start out. There is a problem with young people now. They're forced often to get into a laboratory and for 2 years or 3 years, and then have to find a new position. I would encourage you to try to become an expert in something. Whether you're an expert in AI or an expert in computer graphics or medicine or some field of medicine. But by talking at meetings, by publishing, you get to be known. When you get to be known, you generate collaborators. People come to you because you have a special niche. You have special samples, you have special technology, special knowledge. Then you're expanding because now you're starting at something and you have collaborations and it just keeps going. But the hard part when you jump from lab to lab, which you're forced to do economically, you often get into a different track. And then in the second lab, you're doing something different than the first. The third lab, you're doing something in both of those. And then you don't do you don't want to be a jack of all trades. You want to be somebody special in a particular area.
That's a good advice. Thank you.
We'll use this microphone, right? Okay. My question is for Sir Andrew Geim, sorry. There's a very popular joke among researchers from post-Soviet countries. You may work hard enough, like really work hard, come up with the best research topic you've ever heard of. Then you start researching on similar topics on the internet. You search in English, you cannot find anything. Then you decide to search in Russian. Then you find some published paper in a no-name research journal called Вестник of Barnaul, and then decide and then see what's inside, and you see that it's better, it's more comprehensive. Then you decide to give up on your research career. So it is, of course, it's an exaggeration, obviously, but as a person who come from the Soviet school with the foundational foundational education, you got the you got a global recognition. But are there any researchers like the local researchers, maybe some friends you knew who actually deserve some similar recognition, but they never got one?
To answer your last question, I think everyone deserves what they have, because if you do not push hard enough, you do not get it. So don't get disappointed. Eventually, at the end, you will be there. So don't give too easily. Don't give too easily. But I recognize in the first part of your question, I recognize something which I actually put in my Nobel lecture. It's I got all excellent marks during my university years, but I didn't try to be the model student. So I just try to do minimum, to use minimum efforts to get maximum award. Okay, so this kind of style. But there were people who really were a little bit step above, who were trying to reach beyond the excellence and etc. And somehow they, some of them were never recognized. And one of those, and didn't actually make anything in their life. And speaking at least about some of which, they followed exactly the same style you described. So they had an idea and say, oh, I have an excellent idea. And then they go to a library and look for 2 months in the library what has been done on this subject and say, oh, everything has been done. What's the point of doing that? And then they went back and start thinking about another excellent idea and get to the same result that everything has been done. And the point in this, very simple, whatever you can think of potentially, whatever idea, the best idea comes to your mind, it's someone else has it because we have more or less the same education and many people have the same input exactly as you have. So the point is force yourself, go beyond this initial point of disappointment that everything has been done, because people did this kind of things, ideas. When you go in this direction, which you think is interesting, you make step and you find something new, and then you get another step, you find something new. It can be random walk, as Zuankai just said, okay, not and bring you in completely different direction, but don't be afraid of what happened in the literature. It's if you stop at the moment of investigated literature, you would never get a success, and you don't deserve the success, as I said. Yeah, try to push.
Okay. I remember one story, a scientist Ijima in Japan, he published a paper about carbon nanotube in 1991. The citation, I think now is probably more than 50,000. People always talk, oh, this work can win the Nobel Prize, but so far, no Nobel Prize. The reason is people digged out the first paper about carbon nanotube was published in Russia, not in English, long time ago.
Yeah, 20 years.
Yeah, 20 years ago. That means that Russia really have a deep science foundation. Okay. And also I like your word, use the least effort to have the maximum benefit. I think this is the nature style. Nature use the least material to have the highest energy efficiency. This is the reason why nature is so marvelous. Okay, I think the time is almost up. And the inspiration we got from two speakers are really, really deep. I really learn a lot. I think all the audience probably agree with me. We learned that the great science are not planned. The great science come with small observation. The great science come with the form. Sometimes slow is fast. Sometimes small is big. Hopefully,
Sometimes sick is sin.
yes. Hopefully, you too can continue with Nobel Prize again, and also some audience here can win the Nobel Prize in years to come. Thank you very much.
Thank you. So, Chef.
Time flies. I hope we have time to get more wisdoms from the two speakers. Personally, I can carry away a lot of messages. Okay, I thought I'm an experienced researcher, but after listening to their a lifetime experience sharing, really, some of the issues I need to really think about. Okay, so keep the balance of a professional life and personal life. Okay, that's again very important. Anyway, so I hope today's sharing is inspirational And everyone here, at least we can expand our knowledge in certain area like material science, and also it's inspirational, especially for young people here to plan for our future career. So let's keep our spirit high and hope we can pursue our own scientific dreams and keep pursuit for new discoveries and make our life and the world better. Okay, thank you for coming. Okay, this is the end of the session, the event. Okay, so long. Hoping to see you in other events. Thank you. Bye.